Hi students, welcome back. Today I'm going to talk again about chapter 70.2. That's about characteristics of equilibrium. Yesterday I did a lab simulation with beans, pasta, whatever, to find what is an equilibrium, how can it be assessed. And today we're going to talk about equilibrium expression and equilibrium constant. So when we have the following reaction, I use this reaction lots, N2 plus H2 becomes Na3 in equilibrium. When I have the reaction to the right, we call it forward reactions towards products, and the reaction to the left is the reverse reaction, it's towards my reactants. And we can describe that equilibrium reaction with an equilibrium expression as follows. K is Na3 to the power of 2 divided by N2 times H2 to the power of 3. And K is what we call equilibrium constant. And this total is my equilibrium expression. And those brackets means, remember from last chapter, moles per liter. So more in general, when we have A plus B becomes C plus D with the coefficients, my equilibrium expression, you see it's products over reactants, and my coefficient become powers, because K is concentration of C to the power of C times concentration of G to the power of G, you see from the coefficients here, divided with the concentration A to the power of A times concentration of B to the power of B, my reactants. So products over reactants and coefficient become powers. So that's how we created K is Na3 to the power of 2 divided by the concentration of N2 to the power of 1, but we don't show the 1, times the concentration of H2 to the power of 3, because there's the 3 as a coefficient here, and we see it back as a power. So let's practice this a little bit. We have H2 plus F2 equilibrium 2HF. So products over reactants with my coefficient become powers. So we see here HF to the power of 2 divided by the concentration of H2 times F2. Next one, 2SO2 plus O2 equilibrium 2SO3. Products of reactants, so SO3 over SO2 times O2. And my coefficients, my 2, you see it back here as a power, and the 2 here for SO2 also come back as a power here as SO2, concentration SO2 to the power of 2. So if I have values for my concentration, so expressed in moles per liter, then I can assess the value of K, and that's we call equilibrium constant. So what we do, first we give the equilibrium expression. So we have the same reaction. Some equilibrium expression, K is Na3 to the power of 2, divided by products, divided by reactants, so concentration of N2 times concentration of H2 to the power of 3. Now we plug in the numbers. So we have the concentration of Na3, that's 0.157 to the power of 2, divided by the concentration of N2 to the power of 1, so 0.921, times the concentration of H2, that's 0.763 to the power of 3. And when you calculate it correctly, it's 0.0602. There's no need for unit. It's dimensionless. No unit required. So for this concentration, I can assess my value of K, equilibrium constant. So if I have different values for concentration, look here, I have different values. My equilibrium constant is of course, expression is of course the same, because I have the same compounds. I'm going to plug in the numbers, and I see when I do it exactly, and I see I have 0.0602. Exactly the same value as I have on the previous slide. And that's important, because K is not depending on the amount of reactants and products that are initially mixed together, and also the concentration then. That's not important. What is important for K, the value of K? Temperature. When my temperature changes, my K changes. But it's not depending on the amount of reactants I'm starting with. Always the same K. K only changes when my temperature is different. So, I have an experiment. I think this is also in the book on page 641. I have an initial concentration for experiment 1 and an equilibrium. I see the concentrations here. And for experiment 2, I have my initial concentration. And after a couple of minutes, I have an equilibrium, and then the concentrations are as follow. So we can calculate the value for K. So first, we give the expression, equilibrium expression, SO3 to the power of 2 divided by the concentration of SO2 to the power of 2 times the concentration of O2 to the power of 1, because products over reactants, and coefficient become powers. And then we see my value for the first situation when I plug in the numbers, if I do it correctly, is 4.35. In the second situation, it's 4.32. So almost similar. And that's what I expect because I have no information about temperature, so I assume the temperature is constant. When temperature is not changing, my K will not change. Important to remember. So one more thing I wanted to show you about heterogeneous equilibrium. When I want to set up my equilibrium expression, I'm only going to include gases or solutions, so ions in solution. If I have the following, calcium carbonate as a solid in equilibrium with calcium oxide solid plus CO2 as a gas. So my K expression, products over reactants, my product is CO2. I'm not including these solids, so it's only CO2 that's included. So now I have a precipitation reaction. Ca2 plus CO3 2 minus becomes a solid CaCO3. Products over reactants, but my product is a solid, so I'm not going to include that in my expression. I only include my reactants, calcium 2 plus ion and the carbonate ion. So that's why I have my K is 1 over concentration of Ca2 plus times the concentration of CO3 2 minus. So remember, for the K, products over reactants, coefficients become powers, only include gases or solutions. Particles are in solution, so the AQs. So I want you to study after this chapter 17.2, A and B, and there's a worksheet online on Schoology Equilibrium. Please make those questions and turn it in on Schoology as well. Okay, that's it for today. Bye-bye.